So the topic is a large topic, this issue of the relation between physics and mathematics, and in particular, what I claim is a tension between the two. And this talk is based on an equally simple-minded paper, which is indicated here. It was published in the Journal of General Philosophy of Science. Feel free to download it. It's open access, so it's easily downloadable. I'm following very closely this paper here, but nevertheless, there are some parts of it which I'm not going to address in my talk. Here is the main message of this talk. I usually like to give the main message in the very beginning of the talk, which is a very simple summary of the main philosophical or conceptual message of what I'd like to argue for. And the first part of this main message is that there is indeed a tension between mathematics and physics. I don't think this comes as a great surprise to many of you, although I don't think it's very well known outside of the profession, outside of the smaller circles of those, in particular, philosophers of physics who pay attention to the relation of physics and mathematics. But nevertheless, perhaps it's a non-trivial claim that there is indeed tension between mathematics and physics. The second part of the main message is that I regard this tension both natural and fruitful for both mathematics and physics. So this is not something one should be unhappy about. Quite on the contrary, it is a sign of good health of both disciplines, I claim here. And the final part of the message is that the physicist's ambivalent attitude towards mathematical precision in physics needs perhaps an explanation. I'm going to try to give a quite speculative and somewhat provocative explanation at the end. I don't insist on that explanation to be very acceptable. It's for the sake of the argument there. But I think that the attitude, ambivalent attitude towards mathematical precision in physics by the physicist is a phenomenon which cries out for some sort of an explanation, and I'm putting this on the table as a possible problem here. So this is the main message of this very non-technical talk. I start with formulating what I call a standard view about the relation of mathematics and physics, and this can be summarized in the following way: that physics is science in the modern sense to a large extent because it is systematically mathematical. And by this systematic mathematicity, I mean two things. First, that physics carries out quantitative measurements which aim at determining the values of operationally defined physical quantities. And this is what experimental physicists do. And this is what ensures what I call here descriptive accuracy of physics. But that is just half of physics being systematically mathematical. The other half is that physics sets up mathematical models of the physical world, of the physical phenomena, mathematical models which also incorporate and make explicit the functional relationships between measured quantities. In other words, to put it succinctly, physics formulates general quantitative physical laws, and this is what theoretical physics does, and this is what ensures predictive success of physics. Now, this is a very simplistic formulation of what I take to be the standard view, and a lot should and could be added to this. Clearly, the measurements always have experimental errors. The operationally defined physical quantities are theory-laden. The status of physical laws is, as we know, very problematic. But I'm suppressing all these sophisticated, philosophically sophisticated but important issues. I take that this is essentially a correct characterization of the main relation between physics and mathematics. The point which I would like to emphasize here, that although this view is correct, it is naive in an important respect, important that is for the topic of this talk. Namely, naive because it is based, at least tacitly, on what I call the supermarket picture of the relation of mathematics and physics. And by a supermarket picture, I mean the picture according to which mathematics is very much like a supermarket and physics is very much like a customer. So when it comes to setting up the mathematical models of the physical phenomena, when it comes to formulating physical laws in particular, then what the physicist does is that he or she goes to the mathematics supermarket, has a look at the shelves, takes off a product, a mathematical product, and possibly with tinkering with it and polishing it a little bit after checkout, he has the mathematical tool which he needs for modeling the physical world. And I think this supermarket picture is a bit naive. It's the naivete, again, I'm going to discuss this in a minute, but the essential point is that it is assumed tacitly in this picture, in the standard view, that the mathematical concepts, notions, which are needed for the purposes of physics to set up the mathematical model of the physical phenomena are available, in fact, in mathematics at the time when it is needed for the purposes of theoretical physics, and that they are available in the sense of mathematics, they're available as mathematical entities. And I think that this is naive. This tacit assumption frequently does not hold. The mathematical concepts are frequently not available in the strict, precise, consistent mathematical sense and form at the time when they are needed for physical purposes. Not only that, I think the situation is even more complicated in the sense that it can take a considerable amount of time to create the mathematical concepts which are needed in theoretical physics. But while these concepts are not available, physics cannot stand still. It has to do its work, and during this time, physics then will be necessarily, from the perspective of mathematics, sloppy, imprecise, problematic, even inconsistent. Outright inconsistencies are present in physics. I'm going to support these claims by recalling and commenting on some historical examples, which in my view display this phenomenon, but I call the need for physics and the lack of mathematics, of precise mathematical concepts at a time, the tension of type 1. This is the first type of tension which is present in physics. Again, this is the kind of tension which arises from the fact that physics needs certain mathematical concepts to formulate the physical laws, to formulate the physical models of the world, which involves mathematics, but mathematical concepts which are needed for a proper model are not always available. And when this happens, then a tension is present in physics, and I call this tension of type 1. And again, I will support these claims, the presence of this kind of tension, by recalling some examples from history, examples which are very well known, and I'm only scratching the surface of these otherwise quite interesting and deep historical episodes. I'm listing first the 4 episodes which again, I'm quite sure everyone knows. And I'm going to go into some details about them, but not at great detail. The first example is the concept of derivative at the time of Newton, and the lack of the mathematically precise concept of derivative and the resulting inconsistency of the Newtonian mechanics, which is, as indicated here, a slightly controversial issue. I'm going to say in what sense. The second example is the missing spectral theory of general unbounded self-adjoint operators in the late 1920s, at which time quantum mechanics, and this was before von Neumann cleared up the situation mathematically, the spectral theory and quantum mechanics as a consequence was inconsistent. The third example is the notion of ergodicity, metric transitivity, lack of precise formulation of the concepts needed for ergodic theory made the foundations of classical statistical mechanics before von Neumann inconsistent, or at least it wasn't clear that it was consistent. And the fourth example is the issue of this mirrored quantum field as operator value distribution, a concept which only appeared with Weizmann's work, and before Weizmann's work, quantum field theory was inconsistent. As we will see, this last example is very relevant even today. These are four examples which I'm quite sure you know very well, but I'm also certain that there could be many, many more examples. So I'm putting here 3 dots, and I'm looking forward to hear possibly other examples from you which indicate the kind of tension which I have in mind, tension of type 1. So the first example, very well known and much analyzed, Newton would have needed the concept of derivative of a function for his purposes in mechanics, but of course he didn't have it. So what did he do? Well, he did what he could do, namely he was reasoning in an inconsistent manner. And one can distinguish two styles of reasoning, two types of reasoning. One was algebraic in nature, and that involved the infamous infinitesimals. This is the pre-Principia period in which he was reasoning this way. And the geometric reasoning, or mainly geometric reasoning, which dominate in Principia. And the phrase which he used was the ultimate ratios of vanishing quantities. And that these reasonings were inconsistent and problematic didn't go unnoticed. Of course, here is a Newton expert which mentions this. Miklós Giardini writes in his Cambridge Companion to Newton article that Berkeley was to observe in the Analyst in 1734 that the limits of vanishing quantities employed in the Principia are as mysterious as the infinitesimals, since the ultimate ratio of two vanishing quantities, when the quantities are vanished, is 0/0, which doesn't make sense. And before they have vanished, the ratio is not the ultimate. So this was known already at that time that it was very problematic. And let's just be a bit more explicit about this. At the risk of insulting your intellect, I have recalled here the kindergarten derivation of the speed of a body moving on a straight line in such a way that the distance covered is proportional to the square of the time, and the calculation of the speed of this body is presented here in the form in which you have seen this many times very early on. I said kindergarten, maybe this is a bit overstating, but certainly in high school. And it is this kind of reasoning with infinitesimals, dt, is the infinitesimal here, which is assumed to be non-zero here, and it is assumed to be zero at the end, about which Berkeley says famously the following: for when it is said, let the increments vanish, in the end of the reasoning, i.e., let the increments be nothing, or let there be no increments, the former supposition that the increments were something, or that there were increments, is destroyed. And yet, a consequence of that supposition, i.e., an expression got by virtue thereof, is retained, which by the foregoing lemma is a false way of reasoning, inadmissible. What's the lemma? Here's the lemma, Berkeley states. If, with a view to demonstrate any proposition, a certain point is supposed, by virtue of which certain other points are attained, and such supposed point be itself afterwards destroyed or rejected by a contrary supposition, in that case, all the other points attained thereby and consequent thereupon must also be destroyed and rejected, so as from thenceforward to be no more supposed or applied in the demonstration. And this is so plain as to need no proof. Indeed, this is plain. That is to say, it's plain that there is an outright contradiction in the reasoning which I displayed you. So Berkeley exercises here a completely justified criticism of the Newtonian way of thinking, exposing a kind of inconsistency in the reasoning, which then results in the tension between mathematical precision and physics at the time. Now, I'm fully aware that this is, first of all, well known, and it's a simplistic way of presenting the issue. And although this is standard, I believe, in the history of mathematics, the interesting part of history of science is that if you go back to the period and you have a look at the original sources, you're always surprised, and the picture is is always more complicated. And indeed, there have been studies, in particular by Bruce Poirceau, this Canadian historian of mathematics and historian of Newton, who claims that the standard view, which I have presented you, is a bit rough. This is what he writes in 2001 in his paper, Newton and the Notion of Limit in Historia Mathematica. By 1687, 100 years before D'Alembert and 134 years before Cauchy, Newton had a very clear grasp of the limit concept and was far less confused than most common portrayals have led us to believe. So the picture is complicated and there's a fine structure here, but I think nevertheless, at the end, I'm going to make this claim again. It's a fair claim to say that the notion of derivative was not available in the supermarket at the time of Newton, and Newton was struggling with creating it. Concerning Berkeley's critique of Newton, the picture also is more complicated, and I'm just indicating here that I'm aware of this. We know that the notion of infinitesimal was made precise by Abraham Robinson in the 1960s. His book on non-standard analysis appeared in 1966. And although Robinson regards Berkeley's criticism essentially correct, as it is stated here in this paper, there have been investigations and there are scholars who claim that the situation is much more complicated. This is what Michael Katz and David Sherry write in their fantastic erudite paper in their Cantonese, almost a book-length type paper. They write, Robinson regards Berkeley's criticism of the infinitesimal calculus as aptly demonstrating the inconsistency of reasoning with historical infinitesimal magnitudes. We argue in that paper that Robinson, among others, overestimates the force of Berkeley's criticism. So the picture is more complicated, admittedly, but nevertheless, for the purposes of my claim, I maintain, and I regard this as uncontroversial, that the concept of derivative was needed for physics in Newton's time, but it was not available in the mathematics supermarket. Newton had to struggle creating it. So this was the first example displaying the tension. The second example is more modern. It concerns the spectral theory of unbounded operators before Neumann's time, or around the time when Neumann started working on foundations of quantum theory. The notion of spectrum and its relation to the operator, spectrum of which it is clearly a central concept for quantum mechanics, but these notions and the calculations which involved them were very, very sloppy in the until the late 1920s, early 30s, when von Neumann cleared this up. The first attempt by von Neumann, Hilbert, and Nordheim to somehow systematize quantum theory, as is well known, is this paper which was published in the Mathematische Annalen in 1928. This was based on Hilbert's lectures in Göttingen, 1926. And although von Neumann he was one of the authors there, even in this paper, which is the first attempt to axiomatize quantum theory really, and this is a paper in a mathematics journal, at the end of the journal, the authors make a confession which is, I think, remarkable. In the paper, even in that paper, the situation was not cleared up. For reasons which I wouldn't like to go in, they had to assume the Dirac delta function in their calculations. And at the end of this paper, they write, from a mathematical point of view, the method of calculation is rather unsatisfactory because one is never certain whether the operations involved are really admissible. For this reason, we do not detail them further, but we hope to return to these issues on another occasion. So, remarkably, the authors make the point in the end of their paper that it's not clear whether what they do makes any sense. The conditions under which the calculations are meaningful are not specified. And this is in a mathematics journal, 1928. And as it is indicated here, they wish to clear this up. They wish to return to this issue in later publications. And this happened indeed by von Neumann alone. He published the 3 foundational papers. They are listed here. And it was in this first one that the spectral theory was treated in a satisfactory manner, but not with all the details filled in even here. And the second one is about the thermodynamic of quantum mechanical ensembles, and the fourth one is the probabilistic description, the probabilistic design of quantum theory. It was only in this paper, this one, the last one on this page, published in 1930, in which the spectral theory and the spectral theorem in particular, which also clarifies the relation of the relation of the spectrum and of the spectral resolution to the self-adjoint operator, which has that particular spectral resolution. It's, I think, theorem 36 in that paper, which states exactly what the situation is. So before that paper, before that theorem has been explicitly proved by von Neumann, quantum mechanics was just sloppy, inconsistent assumptions were made that were false, like, for instance, that the spectrum contains only eigenvalues, and this was a mess before von Neumann cleared it up. So it didn't take that long as it took to clarify the notion of derivative in the case of Newton, but certainly there was a period during which the theory was mathematically imprecise, contradictory, self-contradictory, there was this tension between physics and mathematics, tension of the first type. The third example is the example of ergodic theory, again, very well known. The roots, the origins can be traced back to Boltzmann's work, late 19th century. But before 1929, essentially, the theory remained very imprecise, mathematically speaking. It was only after Koopman realized that the measure-preserving transformations in a measure space can be regarded as isomorphisms on the associated Hilbert space that it became possible to even formulate a necessary condition and prove a necessary condition, necessary that is for the meaningfulness of the ergodic way of establishing the equality of the time averages with phase averages. Originally, I don't have to remind you that the original motivation for the ergodic hypothesis was to somehow relate the phase averages to time averages, and the time averages involved a limit, and it wasn't even clear whether that limit exists in any sense, in any precise mathematical sense. This was first proved by von Neumann in his paper, and this was made possible by Koopman's idea that the measure-preserving transformation can be lifted to the associated Hilbert space as an isomorphism of the Hilbert space, and then von Neumann could prove that the limit exists in the associated Hilbert space norm. That indeed this took a very long time is noticed by reviewers. Here is a quotation from a leading ergodic theory expert, Thomas Sass. He writes in a paper which is based on his talk which he gave in the Erwin Schrödinger Institute of Mathematical Physics in Vienna, which was devoted to celebrate Boltzmann's heritage. He writes in 1996, it took quite a time until the mathematical object of ergodic hypothesis was found. Indeed, only in 1929, Koopman began to investigate groups of measure-preserving transformations of a measure space, or in other language, groups of unitary operators in a Hilbert space. So von Neumann talked to Koopman. Koopman told him, why don't you try the ergodic hypothesis in this new framework? And von Neumann could prove that the limit exists in Hilbert space norm. Note that von Neumann, this made possible to isolate the metric transitivity as a necessary condition for the equality of the phase and time averages. But von Neumann didn't prove that the metric transitivity actually holds for certain dynamical systems. He just showed that a necessary condition for the meaningfulness of the problem can be satisfied. Proving ergodicity itself, as we know, also is horribly difficult. And again, quoting from the same paper, 1996, after more than 100 years, ergodicity is still not established in the simplest mechanical model in the system of elastic hard balls, though I expect we are not far from a solution. But as to generic interactions, even the questions are not clearly posed, and it might well be that there will not be a final understanding after the next 100 years either. I'd like to make clear one thing. I'm not arguing here in favor of the ergodic hypothesis as a good way of motivating or establishing the equality of the time and phase averages. So I'm not arguing in favor of the necessity of the ergodic hypothesis from the perspective of foundations of classical mechanics. We all know that this is very problematic. The claim is a conditional one. To the extent ergodicity and ergodic theory was regarded at a time or during a certain time as necessary for the foundations of physics, for the foundations of classical statistical mechanics, the concept was foggy, imprecise. The tension between mathematical precision, mathematics, and physics was there. This was the third example. Fourth example. It was known that quantizing fields was very problematic. Physicists were aware of that. The problem was so acute that this is what Weitmann writes in 1964 about the situation. The quantum theory of fields never reached a stage where one could say with confidence that it was free from internal contradictions, nor the converse. In fact, the main problem of quantum field theory turned out to be to kill it or cure it, either to show that the idealizations involved in the fundamental notions of the theory are incompatible in some physical sense, or to recast the theory in such a form that it provides a practical language for the description of elementary particle dynamics. So this is an explicit recognition on the part of physics, on the part of a physicist, of the presence of an inconsistency, of the presence of the tension which I'm talking about. We know what Weitmann's solution or Weitmann's procedure was. Weitmann's suggestion was, well, in this crunch, in this difficult situation, go axiomatic, which means following essentially Hilbert's advice from 1900, separating the mathematical model and physical interpretation of the mathematical model sharply and explicitly, stipulate the mathematical axioms for the mathematical model, and show that the axioms are consistent by creating models. This was the precept which Weitmann successfully followed. And in order to be able to do that, he had to formulate, in particular, the notion of quantum field explicitly. And the key concept in that formulation was the smeared quantum field, which mathematically speaking was an operator-valued distribution. So what his idea was that a quantum field should be regarded as a map which to any function in the Schwarz test function space, these are the smooth, fast decreasing functions, one associates an unbounded operator phi of f in such a way that if you sandwich this unbounded operator by two elements on the Hilbert space on which this unbounded operator is defined in a meaningful manner, taking phi from the domain of definition and psi being arbitrary, then in this way you create a map which is a tempered distribution in the sense of distribution theory. And this is a smeared theory because instead of assigning an operator to singular space-time points, to associate an operator to these functions which smear the operator over the space-time. Weitmann formulated axioms which involved this notion of field, and the next 4 slides contain these axioms, but it's not my intention to go through them. They are there so that if we want to return to them in the discussion, we can do so, but I don't intend to discuss it in any depth, so I'm skipping them over. Here is 1, 2, 3, and 4. And I just would like to point out some lessons from this treatment by Weitmann. The first is that the consistency of the Weitmann axioms could be shown by constructing models, free fields were the models of the axioms, so the axioms were consistent. But this was only possible, the formulation of the whole theory was only possible because the notion of distribution was already at that time available. I mean, before the notion of distribution, of temporal distribution was available, which was the late 1940s and 1951, the book appeared which described Schwarz theory. The consistent concept of quantum field as an operator-valued temporal distribution, which was needed for the mathematically consistent model of quantum field theory in the Weitmann sense, had not been available. So the supermarket, again, proved to be not sufficiently well stocked for the purpose of physics. There was this tension, and this was relieved to a large extent by Weidmann, making use of this concept. And the third remark in connection with this is that constructing mathematically precise models of interacting quantum fields in 3+1 dimension is still an open problem. So the issue, this kind of tension, is not just of historical interest, it is an acute tension. I just would like to quote here two authorities. One is Friedenhagen, Rehren, and Seiler. In their review paper, Where We Are, 2007, they write, despite these successes of the standard model, however, establishing the standard model or part of it as a mathematically complete and consistent quantum field theory remains an unsettled challenge. And another authority, Stephen Summers, writes in his review of constructive quantum field theory, though it, that is to say quantum field theory, has undergone a long and complex development from its origins and has attained an ever-increasing theoretical sophistication, it is still not clear in which sense the physically central quantum field theories such as quantum electrodynamics, quantum chromodynamics, and the standard model are mathematically well-defined theories based upon fundamental physical principles that go beyond the merely ad hoc. So the tension, which this fourth example, it has not just historical interest, it's, I claim, an acute tension in the current state of physics. I would like now to claim that this tension is not something one should be very unhappy about, that it's very natural in a sense. Namely, this tension drives mathematical development. And this was very nicely formulated, again, by none other than one of our heroes today, John von Neumann, who says in his famous little paper, The Mathematician, that the most vitally characteristic fact about mathematics is, in my opinion, its quite peculiar relationship to the natural sciences, or more generally to any science which interprets experience on a higher than purely descriptive level. It is undeniable that some of the best inspirations in mathematics, in those parts of it which are as pure mathematics as one can imagine, have come from the natural sciences. So this is a position, a particular position about the origin of mathematics, which is not unique in the sense that there have been many other mathematical physicists, theoretical physicists who have taken this position. Here are a couple of quotes that indicate this. David Ruel, he writes, "The importance for pure mathematics of ideas coming from theoretical physics is of course well known. The physical ideas of equilibrium statistical mechanics have richly contributed to the mathematical theory of smooth dynamical systems with the concepts of entropy, Gibbs states, so on and so forth. See my paper in the Bulletin of the American Mathematical Society." Another example, another mathematician, Karin Uhlenbeck, writes, "The relationship between physics and mathematics has been fundamental to both for a long time. The gap between the two is significant primarily in this century, as pure mathematics became very abstract, experimental physics became very expensive, and the world became more complicated. However, even through this century, mathematics has relied on physics for input quite steadily. I'm sure other replies will point out the influence of mechanics on calculus, optics on Riemannian and symplectic geometry, general relativity on differential geometry, quantum mechanics on functional analysis, geometric optics on harmonic analysis, and gauge theory on four-manifold topology." So the von Neumannian position is not at all singular. Many mathematicians have taken that position, but maybe not all. And let me just draw some consequences of this position and indicate that this is not something which is necessarily appreciated by everyone. One consequence of accepting that this type of tension drives mathematical developments is that it makes understandable and not at all mysterious that mathematical concepts apply effectively in physics. Quite contrary to what Wigner famously says in his paper, much discussed, Unreasonable Effectiveness of Mathematics in the Natural Sciences, in which he writes, the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious, and that there is no rational explanation for it. I think this position, which was taken by von Neumann and Uhlenbeck and Ruel, shows that this is not mysterious at all. It is only a mystery if you somehow separate too sharply mathematics and physics, and you do not regard the tension of type 1 as something which drives mathematical development. Clearly, it would be perfectly unreasonable if mathematics were not effective on this position. A further consequence of this position, namely that one accepts that the tension of type 1 drives mathematical developments, and the point which I made in the very beginning, that it might take a lot of time until a mathematically non-contradictory, clear concept is created, is that even mathematics can be sloppy, imprecise, and inconsistent, which might be quite an unreasonable position, but it's not. And again, here is von Neumann, and I'm also going to quote some others, who have taken this attitude, a very relaxed attitude towards precision in mathematics itself. Von Neumann writes, and he writes this being influenced by the incompleteness theorems of Gödel, it is hardly possible to believe in the existence of an absolute immutable concept of mathematical rigor dissociated from all human experience. I'm trying to take a very lowbrow attitude on this matter. Whatever philosophical or epistemological preferences anyone may have in this respect, the mathematical fraternity's actual experiences with its subject give little support to the assumption of the existence of an a priori concept of mathematical rigor. And the mathematical fraternity's actual experiences refer to the incompleteness theorems of Gödel, which made it impossible to prove the consistency of mathematics in his view. But here are some other views in the same spirit. Atiyah says, the history of mathematics is full of instances of happy inspiration triumphing over a lack of rigor. Euler's use of widely divergent series or Ramanujan's insights are among the more obvious. The marvelous formulae emerging at present from heuristic physical arguments are the modern counterparts of Euler and Ramanujan, and they should be accepted in the same spirit of gratitude tempered with caution. Very nice words. So these are the consequences if one accepts the idea that the tension is driving mathematical development. I think many more examples of this tension could be given. I would be happy to learn about more examples. And since I think there are many more, this widespread presence of this type of tension indicates to me that this presence is very normal. This tension is very normal. It's not an unusual phenomenon at all, happens regularly and belongs to the normal mode of how physics and mathematics develops. And these examples, I believe, also show an important feature of this type of tension, which I find important to emphasize, not to be misunderstood. Namely, that the mathematical imprecision in physics, which causes this kind of tension, is not an anything goes kind of uncontrolled irrationality, but something which I call here disciplined sloppiness. So there is deep disciplined intuition involved in the unsharp, inconsistent notions, which is shown by the examples, because after possibly a long development, that intuition could be turned into precise and non-self-contradictory concepts. So, in sum, I regard this tangent, the presence of this tangent, which I think is widespread, not a sign of a trouble, of some unhealthy state of matters. Quite on the contrary, it's not a sign of trouble, but a sign of good health of both disciplines, I claim. So this was about the first kind of tangent, but there's another kind as well, which is related to the fact that even when the precise mathematical concepts are available in physics, physicists typically do not aim at mathematical precision. Some physicists claimed explicitly that mathematical precision is not useful, irrelevant, illusory, or impossible. And there are probably many other negative adjectives there that characterize physicists' attitude. I'd like to now indicate or prove that this attitude is indeed present in physics. And this kind of tension, which is related to the physicists' rejection of mathematical precision or the importance of the mathematical precision, I call tension of type 2. Here is Geoffrey and Queen. They characterize this dismissive attitude by writing, "The typical attitude of physicists towards mathematics is illustrated by a passage from a book by Anderson." And the passage from the book is, "They are talking here about theoretical physics, and therefore, of course, mathematical rigor is irrelevant and impossible." And this is from this famous paper by Geoffrey and Queen, in which they voiced their worry about the lack of mathematical precision in connection with string theory, which prompted a debate in the Bulletin of the American Mathematical Society in the 1990s. And the replies to this paper were the papers from which I quoted Atiyah and also Uhlenbeck. So this is one instance. Landau says in his statistical physics book, "No attempt has been made at mathematical rigor in the treatment, since this is anyhow illusory in theoretical physics." Here is another, Feynman. "The mathematical rigor of great precision is not very useful in physics, but one shouldn't criticize mathematicians on this score. They are doing their own job." Here is another one. Thiering reports the following, told him by Pauli. "Pauli once told me that he had said to von Neumann, 'If a mathematical proof is what matters in physics, you would be a great physicist.'" Thiering disagrees with this, of course. He says, "I think he, von Neumann, had the right vision of what will become important in physics." So there is this dismissive attitude, undeniably, there. And this is also reflected by the fact that the status of mathematical physics is a bit controversial, socially speaking. And mathematical physicists find themselves doing something non-standard and weird. This is nicely expressed by Weitmann, again, one of the prominent mathematical physicists, when he characterizes how he felt when he was doing constructive axiomatic quantum field theory. He writes, quotation is from the same book, "The physicists who have engaged in this kind of work, doing axiomatic quantum field theory, are sometimes dubbed the Feldverein. Cynical observers have compared them to the Shakers, a religious sect of New England who built solid barns and led celibate lives, a non-scientific equivalent of proving rigorous theorems and calculating no cross-sections." Now, you probably know that the Shakers were a particular sect which flourished into the 20th century. This is from a page, when celibacy took its toll on the sect and their numbers dwindled to near extinction. one of the last proud villages was the City of Peace, or Hancock Village, which became abandoned. So what effectively Weightman says, that mathematical physicists are a weird, endangered species doing unusual work, not at all mainstream. Here's a picture of Hancock Village. So the presence is there, this tension between mathematics and physics in this second sense, type 2. And I'd like to discuss now, address in the final part, the issue as to why physicists don't like mathematical precision. And I think there are two intuitions in this dismissive attitude, one which is good and the other is not good. The good intuition is that it's true that striving for mathematical precision is not the main source of development of physics. It's not the decisive source. Experimenting, observation is. But this good intuition gets intertwined with the wrong aspect of the intuition. And it is that mathematical precision is not useful epistemologically because it does not contribute to the development of physics. And I think this is wrong. So the dismissive attitude is the result of not separating nicely and clearly these two components of the intuition. One component I think is acceptable and good, and the other not. I claim that mathematical precision does contribute to the development of physics. That is to say, I try to argue very briefly here why the wrong component of the intuition is wrong. And this is mainly because mathematical precision forces conceptual precision and clarity. Or if you want to be less aggressive in your formulation, you can say that mathematical precision leads to conceptual precision and clarity, is conducive to, facilitates it. How? In an obvious manner, I believe, namely separating the mathematical and the non-mathematical part of your theory requires to make the link between the two very explicit and ambiguous. And also it requires you to make the physical and mathematical assumptions explicit. And there are many of them in theoretical physics. Idealizations, neglections, approximations are all prevalent, and making them explicit just helps. Also, if you achieve structural systematicity, hierarchy within a theory, which the axiomatic approach clearly achieves, then you have clarified conceptually your theory tremendously. And also, mathematical precision can contribute to the clarification of relation among different physical theories. And more generally, this attitude forces self-reflection when your aim is not just to be able to describe and predict, but also to make sure that your theory itself is okay. So this self-reflectiveness is forced upon you by the mathematical precision. And I claim that all these are epistemological virtues which are different from, and in addition to, what I stated in the very beginning, were important, namely descriptive accuracy and predictive success. So repeat the claim, there is a wrong component of the intuition, and it is wrong because it is assumed wrongly somehow that mathematical precision does not contribute to the development of physics. The final slide essentially is asking why it is difficult to get rid of the wrong intuition. Why this dismissive attitude then? A speculative answer is here the following. As I have argued, mathematical precision forces conceptual precision and clarity, but this conceptual precision and clarity also makes it clear what is not clear at a given time, conceptually, in physics. In other words, the mathematical precision exposes the fundamental limits of a physical theory at a given time, makes them explicit. And since at that time, it might not be possible to go beyond those limits by creating better theories, this is epistemologically frustrating, obviously. And this can be also psychologically frustrating. It can be perceived by the actors, by the physicists, as limits of their own subjective capabilities, limits of their cleverness, ingenuity, creativity, and intellectual power. And of course, no one wants to experience these sorts of limits, because this can be very unpleasant, and it can also be perceived as an existential threat even, and it's perfectly understandable that physicists do not wish to experience it, so they reject it. This is my speculative and provocative answer to the question as to why it's difficult to get rid of the wrong intuition, which leads to the rejection of mathematical precision in physics. If I may summarize, so I claim that there exists a tension, or can exist a tension, between physics and mathematics due to the fact that precise mathematical concepts needed by physics at a given time might not be available, and developing them needs time. I also claim that this tension is useful for mathematics. It drives its development. I also claim that there exists a tension between mathematics and theoretical physics due to the fact that some physicists have the questionable intuition that mathematical precision does not contribute to the development of physics, and the prevalence and persistence of this problematic intuition can perhaps be explained to some degree by the fact that mathematical precision can make explicit the limits of physical theory, which might not be overcome at a given time, and this is both epistemologically and psychologically frustrating. Thank you very much, and I'm looking forward to other examples and challenges of the claims I have made. Thank you.